Hello, I welcome you all to this class. Now today we are going to discuss about the shear force and bending moment diagram. That already we have discussed the types of beam, types of load, okay, and the sign convention in the shear force and bending moment diagram. So here we'll go to the next topics. That in this class we see the relation between load, shear force and bending moment, right? So if I recall you that previous class in about the shear force and bending moment diagram, that we have a 5 types of beam: simply supported, cantilever, fixed beam, continuous and overhanging beam. And 3 types of load will act on a beam: that point load, UDL and UVL, right? So as well as we have discussed that how to take the sign convention while we draw the SF and BMD diagrams right now. So now in this class we are going to generate the relation between shear force, load and bending moment. So for that we have taken one beam, right? And on that beam the UDL is acting. UDL is nothing but a uniform distributed load, right? So here you can see on the screen that you have a one beam is there, that this beam is here we have taken of AB name right now, and on the beam this UDL is acting, right? So this is the symbolic representation for the UDL, that is uniform distributed load. Over the UD means beam, the load W load is acting per unit length, right? Means what? For one length, means for 1 unit length the Newton of load is acting. Okay, so uniformly distributed load means what? That which is distributed across the length, right? So first of all, for generating the relation between load, shear force and bending moment diagram, what I'll do, that we have to consider one section, right? So we are considering one section here on the beam. Let's say this is section 1, right? And the another section we have a 2, right? So these are two section we have considered, section 1 and a section 2, right? Now in this section the small portion of the beam we have taken, that this is the small portion of the beam, this much of portion we have taken. Over that the UDL is acting, right? So let's say that the length of this portion is nothing but the dx, right? So let's say the length of the portion which we have taken, that is the dx, right? So if I see, then the forces has to act, right? So let's say this is your axis. So on this on the section 1 the shear force and bending moment will act, and as well as on section 2 the shear force and bending moment will act, right? So you can say let's say the F force, that shear force at the section 1 is acting vertically vertically up at section 1, and the moment, right, and the moment of having magnitude M is acting on the section 1 clockwise, right? Now similarly when we come to the section 2, that at section 2 that shear force will be vertically downward, right, and of having magnitude is F plus df, right? F plus df, and the bending moment will be the anti-clockwise of having magnitude is M plus dm, right? So this is what we have considered. So now you can see that we have a beam, any beam is there. So here we have taken simply supported beam. Why? Because the two supports are there, that one support is at the end A and another support at B, right? So we can say a simply supported beam carrying UDL over the length, right? So now from that section of from that beam we have chooses one small section of having length is dx, right? And then at the section 1 the shear force is F, it is acting vertically up, and the bending moment M is acting clockwise. Similarly at the section 2 the shear force is F plus df, it is acting vertically downward, and the bending moment M plus dm, which is acting anti-clockwise, right? So now we can write these all data whatever we have considered here. So you can say let F is a SF means shear force, right? Shear force at the section 1 1, right? And F plus dF is the shear force at the section 2 2, right? And M is the bending moment, bending moment will write in the short, that is BM, right? Bending moment at section 1 1, right? And M plus dm is the bending moment at the section 2 2. All right, now then we can say the we have a forces and moment acting on the length dx. This is what we have considered, right? So the forces act means here only you can say that F shear force at the section 1 1 is vertically up, and F plus dF is the shear force which is acting vertically downward on the section 2 2, and the M is acting at section 1 1 clockwise, and M plus dm is acting anti-clockwise at the section 2 2, right? So this section dx which we have taken, it is in equilibrium right now. So now first what we will do, that we can resolve the vertical forces, right? So if you look at the vertical forces is what? The vertical forces is nothing but the that shear force F at section 1 1 vertically up, and the shear force F plus dF, it is at the section 2 2 vertically down, as well as the UDL is acting on the section which we have considered here right now. So it means that this on this portion also we have a W amount of load is acting, that is UDL is acting over the dx length, is it or not? So whenever the UDL is given, we need to convert this UDL into point load. How to convert the UDL into point load? To convert the UDL into point load, we need to multiply the load with the length, means over which the load is acting. So in this case the load is acting up to a dx, right? So when you multiply this load to this distance, it become point load. Why? Because whenever do the calculation, the UDL first should be converted into the point load. To convert the UDL into point load, we need to multiply the load into distance, right? So it means that this load will act vertically downward. Okay, so O means on this section dx, the three forces are acting, that is two are the shear forces, and the one is the load which is acting because of the UDL, and F is acting vertically upward. W dx will act in the, that is which will be become point load. W dx will act in the downward, and F plus dF will act in the downward, right? So when you resolve the forces, so resolving the forces vertically means what? We have to apply the equilibrium conditions. So equilibrium condition, three equilibrium condition you know, that is summation of Fx is 0, summation of Fy is 0, and the summation of M is 0. So Fx means what? That on a given section, sum of all vertical forces will be 0. Okay, if we have summation Fx, right, means sum of all horizontal forces on a given section will be 0, and summation of M means summation of moment is 0, means what? The sum of all the moment will be 0. So these things, if these three conditions will satisfy, then we can say the section or a body is in the equilibrium condition. So as we have considered that the given section, means the section which we have taken dx, it is in equilibrium. Equilibrium means what? It must satisfy the three conditions, which is summation of sum of all vertical forces, sum of all horizontal, and sum of all the moment should be 0. So first we say that the sum of all vertical forces is 0, right? So means you resolving the forces vertically. We don't have any horizontal forces, so we don't write that one, right? So first we can say here that resolving the forces vertically, right? Resolving the forces vertically. Okay, so when we resolve the forces vertically means what? That you can see here the three forces is there. F is vertically up, F plus dF is down, and the W into dx, which will become the point load, will also downward. So downward is negative and upward is positive, right? So here you can write that F, right, it is positive, minus W into dx, this is UDL, and when you multiply this UDL with the distance, it becomes the point load, minus F plus dF, as it is the equilibrium condition. So summation of Fy is equal to 0, means sum of all vertical forces, their sum is 0, right? So when you open this, so F and this plus F and minus F will get cancelled. So let's cancel them. So this and this will be cancelled, and it minus and plus will become minus. So here you can equation will become like this, that is minus W dx, right, minus dF is equal to 0. Okay, so after cancelling the F and F, the equation will become like this. So now you can say dF is equal to minus of W dx, right? So now dF, that further dF by dx is equal to minus W, right? So this is what we will got. Means you can say the above equation, what is this telling? That the equation is tells that the rate of change of shear force is equal to the rate of loading, right? Means rate of change of shear force means what? F is the shear force. Shear force is differentiating with respect to, when you differentiate the shear force with respect to the x, means with respect to the position, you will get the rate of loading. Rate of loading is nothing but the UDL, right? Now, so now you can say that here we'll see, wait. So the above equation we got that dF by dx is equal to minus W, right? So this is your first relation we got. The relation between what? The relation between shear force and the load. Okay, so we can say the above equation shows that the rate of change of shear force is equal to rate of loading. Okay, is equal to the rate of loading, right? So that first relation we got. Now one more relation we have, that if you look at the topics, that the relation between the shear force, load and the bending moment. So the between shear force and load we got the relation. Now we have to get the relation between shear force and the bending moment. Okay, so here we can see that in the same portion, I'll draw the portion, that whatever the portion we have taken right now. So this much of portion we have taken of having thickness is dx, right? On that portion the load is acting, that is W unit per unit length of UDL is acting. So let's say this is the section 1 and this is the section 2, right? So it's better you can say here, and this is section 2, right? Now, so and on this is the axis, right? So this is the section 1 and this is the section 2. So here the shear force, the vertically up shear force is acting of having magnitude is F, and the moment is acting towards clockwise of having magnitude is M, right? And then the shear force at the section 2 is acting, which is the F plus dF, and the moment is anti-clockwise, that is M plus dM, right? Now, as well as one more moment will act if I find the moment because of this UDL, right? So that moment is nothing but the W into dx, right, into dx by 2, right? Now so first of all, what we need to do, that any section you can choose, either the section 1 or section 2. About that section you can say the moment will be 0. Is it or not? Now you can say that I'm considering the section 2, right, and taking the moment about the section 2, right? So we can say so you can write here that taking the moment of the forces about section 2, right? So we are taking the moment of the forces about 2. So what are the forces you have? That is, one force is F, another force is F plus dF, another force is W, and the two moments are there, that is M and M plus dM, right? So we need to say that this is what, that if I take this force, that is if I take the force F, right? So for force F, the moment, if we have chosen the section 2, right now, so we have chosen the section 2. Okay, so for about 2, about this section 2, the moment about the force is what? So F into distance, force into perpendicular distance is the moment. So force is what? The vertically up, and the distance is the horizontal, that is dx, right? Sorry, this is the dx, right? So F into dx. Again, one moment is already acting, it is clockwise, so these two forces are having same sense, right? And then this is what? F plus df. We can't take this force. Why? Because the moment we are taking about this position only, at the section 2 only. But we have a one moment is there at the section 2, which is M plus dm, which is going anti-clockwise, and one more moment about the load udl at a distance of dx by 2, right? Why? Because see, whenever we'll convert the UDL into point load, that the question is acting, see, actually now the UDL is there, dx, means the UDL is acting up to a length of dx. When you convert this UDL into point load, what you should do? You need to multiply W into dx, that become point load, right? Then the question is arising where the point load will act. So point load is what? The point load is a point where the point load is acting at the one point, right? Now, so where that point? So whenever the UDL is converted into point load, that point load will act at the center of gravity. Okay, so if I see, this is the section dx right now. So where is the center of gravity? The center of gravity will be the mid of the span. Mid of the span means what? Dx by 2. It means that this W into dx will act exactly at the half, means dx by 2. So when you find out the moment about this W into dx, that will be W into dx by 2. Okay, now then you can see the clockwise moment is here, that is the clockwise moment will be the positive, and negative, and the anti-clockwise moment will be the positive, right? So now let us do that. So say here you can see, first I'll tell you that this will go F, and when it is, you are finding the moment about this, it will turn like this, means clockwise, right? And M is also clockwise. When this W is acting downward and you are finding the moment about this one, so it will be anti-clockwise, and this M plus dm is already anti-clockwise. So anti-clockwise moment I am going to take positive, and the clockwise moment I am going to take the negative. Okay, now so we have already written that taking the moment of the forces about the section 2, right? So directly you can write the moment is at the section 1, first is M, which I'll take it as a minus. Why? Because clockwise I took as a negative, minus F into dx, okay, plus W into dx. This W into dx is now its point load. Where this point load will act? This point load will act at the mid of the span, that is dx by 2. Okay, now then you have a one more anti-clockwise moment, that is M plus dm, okay, and that should be equal to 0. Alright, this is the equilibrium condition we have satisfied, means what? Summation of M is equal to 0, right? So summation of M is equal to 0 means this M, wait, so minus M and the plus M will get cancelled. What remain? So remain is minus F dx, okay, plus W into dx whole square by 2, okay, and plus dm is equal to 0. Right now then you can say further that is so this f minus f dx is equal to minus wait, see, then the equation is what? Minus f dx plus w into dx whole square by 2 plus dm. So if you see that dx is a very smaller quantity, right? So you can say that the higher power of a smaller quantity we are neglecting. So this is what? This is the high power is 2, and this dx is a smaller quantity. So the neglecting the higher power of a smaller quantity. So when you neglect the higher power of a smaller quantity, it means that this whole term will be negligible from the equation. So the remaining is what? F dx and dm. So here you can write down the statement, that will be better. Okay, so neglecting the higher power of smaller quantities, right? So when you neglect this higher power of a smaller quantity, the equation will become like this, which is minus of f dx plus dm is equal to what? 0, right? So then this is there. So now wait, come back. So your equation is like that further you can write, let me check, minus f dx plus dm, right? So the equation is minus f dx plus dm is equal to what? 0. So when you bring it this side, minus minus get cancelled. So f dx is equal to dm. Is it or not? Now, so then you can say the dm by dx is equal to f. Means what? It means the rate of change of moment is nothing but the shear force, right? So the above equation shows that the rate of change of moment is equal to the shear force. So you can write down the statement. You can write the above equation says that the rate of change of moment is equal to shear force, right? Is equal to the shear force. Means also while we draw the SF and BMD diagram, we can find there is some point where the shear force is become 0, right? So whenever we'll get the position, means the point where the shear force is become 0, at that point the bending moment will be maximum. So if you see this is what dm by dx is nothing but the f. It means what? That you are differentiating the bending moment with respect to x, and if you know the maxima and minima condition in your engineering mathematics, that whenever you have to differentiate any function with respect to x, right, and then equate it with 0, you'll get the maximum function right now. So it means that you can say bending moment will be maximum at the point where the shear forces become 0. So you can say bending moment will be maximum at the point where shear force is 0, right, where the shear force is 0. So this is what the conclusion of the derivation means. The two relation we generated, one is what? That one is nothing but the rate of change of shear force is nothing but the load, right? That you have a df by dx is equal to load. This one relation we got at the starting. The rate of change of shear force is nothing but the rate of loading, and the second is nothing but the rate of change of moment. That bending moment is equal to the shear force, right? So these are the two relations which we have derived in case of the shear force and bending moment. Thank you.